Okay, here we go. Okay, so, you know, one of the things with room temperature superconductors is they don't get hot. I'm holding this, zooping on it with high friction. My finger's right underneath of that. Try that with a piece of steel. See what happens. In case you think I'm not actually doing it, I am actually doing it. This is my finger. Got a little warm there, a little bit. About 3 degrees warmer. I can hold this in my hand. Immediately, it's cold, it's cool. What that means is if I make an engine out of this and I start producing heat from my combustion chamber, it's just gonna sit inside there, and I'm not gonna waste a lot of the energy into wasted heat leaving through the through this stuff. And this stuff won't get hot and expand. Right? It doesn't get hot, it's not going to expand. Which means that, well, for instance, if metal expands, what's going to happen to this hole here? It's going to get smaller, isn't it? Not going to get bigger, it's going to get smaller because there's more metal pushing in on it. And that means that the specifications of something that turns inside that hole has to accommodate the expansion and contraction of the metal around it and in it. Right? So if I make my axle, or the thing that goes around and around with this stuff, and I make the outside part with this stuff, it's not going to get hot. Not with anything in normal use. You know, what I just showed you was a pretty good demonstration of what room temperature superconductors do. Okay, it's not just conducting electricity. This passes magnetism without resistance. Now, you know, most people just don't know enough about magnetism to understand that particular statement. If I take a piece of steel that's as thick as this piece of platinum, and I put a magnet on this side, and I try to pick up this iron rod on this side, gosh. Oh, well, maybe it's not magnet. Okay. Maybe I better find one. Okay, that thing is magnetic. So let's find out if we can make it come up just a little. There it is. Ooh. So anyway, passes magnetic current, magnetic energy, with very little or no resistance. Certainly none that I can determine with the measurements I have available to me in my funky little laboratory here. I can't find any, and I've also measured it for resistance for electricity and can't find any. I get a 0 ohm reading when I use the highest setting with the most the finest measurements I've got, 200 times more than the ambient. It's maybe even more than that. I don't know, 2,000 times, something like that. It's a lot. And the thing with platinum is that you can make it into wires, and you can print with it in a 3D printer, and you can make this stuff into anything you want to, because it's not really rare at all, right? This stuff started out as dust in the road. My wife picked it up. I put a piece of Chinese steel called teals of silver. Chinese silver is generally, the older stuff, at any rate, was alloyed with a little bit of gold. But this is recent, modern stuff, and each one's got a little swastika on it, man. And I think it was made during World War II, and it's light. It's not sterling silver quality. It is not 975 silver. It's about 850, something like that. It's got silver in it, you know, that sort of thing. And copper, you can see the copper when I start hitting it with the torch, and gives a kind of a greenish glow as it vaporizes. But the silver and the copper vaporize, right? They're gone. This thing was a puddle, a liquid puddle of metal sitting on top of the AUPT dust. And metals have the property of pulling or moving towards the heat rather than away from the heat. So the metal is actually pulled into the silver as the silver evaporates, and that's what it's doing. It's literally evaporating. And what it does is, first of all, it pulls in things as the temperature goes up. It starts pulling in gold through the crystal lattice, right? The separate bits and pieces of the crystal move away from each other, and it allows the vapors of gold to move in. And the vapors of gold are attracted to that heat. So they move in, and as they move in, they're pulling the palladium in. That's the next thing in, and that's the really shiny silver stuff here. And then platinum. And the platinum is the darker colored silver stuff. You know, like this in here. This stuff in here. And you can see when it was forming, there was some movement of gold into there, and then these lighter specks are the palladium, and they're in a fairly regular arrangement, because this was liquid, right, and it turned into a solid in about 3 nanoseconds, 3 billionths of a second. Um, and the palladium was not incorporated in the AU and PT. AUPT, 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 because those share a double covalent bond. Um, and the palladium is excluded from those, right? It's not like alloying with the AUPT. It's just there. It's present in the dust. And what happens is the crystals form with the AU and PT around the bits and pieces of palladium. And so that's what you see there is the bits and pieces of palladium at the kind of intersections of the crystal lattice. So it's got planes of cleavage flowing through it, going through it, and they move, and their direction is in all three directions, X, Y, and Z. And the gold moves through there like water through a sieve, basically. And that puts the gold in there, and then as the gold starts to evaporate, and it does, big time pretty much, then the palladium gets pulled in. And as the palladium evaporates, it just leaves the platinum and gold. So I can purify this by just heating it for longer periods of time and blowing away all the gold and platinum. And I'm looking at some equipment out of Oak Ridge, Tennessee, the breeder reactor there, where I can get a bell jar thingummy. It's got a coil wrapped around it for precipitating out the stuff as it comes off in a vapor, and that coil draws it onto the into the magnetic field there, and you can create crystals of gold and platinum and whatnot as they recondense from the melt, from the vapor. So it's like a vapor disposition thingummy, and I can buy the darn thing pretty cheap. It's government surplus. So we're looking at these things, and I don't really want a funky laboratory, man. I want a really nice laboratory, and so we're going to sell some of this stuff and buy some of that stuff. And I think what I want to see is what it does, like it is, right? Because the first thing everybody asks me is, how do you separate it, right? Because everything they know is just separate. But you know what? It's not coming apart by itself, and it doesn't come apart easily at all. Plasmas are a rather recent addition to the stuff, the kind of technology we have available, widespread things like these plasma cutters. Man, I paid $135 for a Cut 50 plasma cutter. And that's what's separating double covalent bonds in the AUPT dust. Otherwise, it just sits there. If I put this in my induction furnace and I run the temperature up to 1768, it just sits there. there's not enough energy to break those double-double covalent bonds. And that's what the issue is. You have to break those bonds in order to change those metals into something that we want to use with metallic bonds, right? They have covalent bonds. Some of them are, you can see light through it, right? It's a metal, but you can see light through it. That white stuff, that people call quartz, that's what it is. It's platinum. It's not quartz, folks. Quartz doesn't make cubes, doesn't have planes of cleavage, and melts at 1250 Celsius. And the ones with double covalent bonds require 3000 degrees Celsius to break those suckers. That's why I have platinum and palladium and gold from the dust in the road. Not even on the side of the road, man, right square in the middle. And it is a room temperature superconductor.